Okay, so welcome back, guys. Actually, I will go back a couple slides here. Just want to review some things we did yesterday. Oops, I didn't go back far enough. We looked at yesterday 3 ways to calculate concentration. We looked at molarity, which is like the chemistry way, where you would calculate moles of solute per liters of solution. And then we would look at mass percent and parts per million. They're honestly, they're the same calculation. The only difference is with mass percent, we're multiplying it by 100%, and parts per million, we're multiplying it by 10 to the 6. You can think of it like percent, we're converting it into a percent. Parts per million, we're converting it into, well, a million. That's what 10 to the 6 is. It's 1 million. So unfortunately, because of time and I had a lab and everything the other day, I didn't get to do this last example, which I'll show you now. And then I'm going to give you a practice problem that will hopefully kind of bring it all together for you guys. So let's look at this question. A solution which contains, and this is actually a little harder question. I'll explain why in a second, sorry. A solution which contains 1.5 milligrams of solute in 2 liters of solution. So we have the entire solution here, has a concentration of, and I should mention, I remember Aman yesterday actually brought this up. When you guys get this question, I will mention, I don't know why I can't write, that I'm asking for ppm or I'm asking for percent. So like when you get this question on a test or final exam or something, or in the lab next week, actually, lab number 9, I'll be specific. I'll say calculate the concentration in percent or moles per liter. Anyways, this is in ppm. The problem with this question is that we're given 2 different units here. We're given liters and milligrams. And really what we want to do for percent or ppm is we want to change it to grams. Now, you actually don't have to do this, but it just makes your life easier for trying to use all of these formulas or remembering all of these formulas. So just remember, actually, this has some unit conversion tricks in here. One thing is that 1,000 milligrams is equal to 1 gram. Oh, my pen. So to convert milligrams to grams, we would divide by 1,000. Okay, now the 2 liters is a little bit more complicated. 2 liters is equal to 2,000 milliliters. Let me explain how I know that. Let me just erase that. I'll explain where I'm getting that number. 1,000 milliliters is equal to 1 liter. So that means this is 2,000 milliliters or 2,000 grams. Remember, grams and milliliters are interchangeable, so I can just convert the milliliters to grams. So now think about my information. I have the mass of my solute in grams, and I have my mass of my solution in grams. So here's my mass of my solute in grams. Again, all I did was divide by 1,000. And here's my mass of the solution in grams. So all I do is plug this information into my equation. Probably shouldn't be using red here, should I? Let me pick another color. So I divide by 1,000. And then I take these 2 numbers and put them into my equation. And that's really it. All right, so mass of your solute over mass of the solution. This should say solution. times 10 to the power of 6, and you get your parts per million. It's typically a pretty small number. Okay, so let's put all of this together. Oops, I didn't mean to do that. Okay, I am going to stop sharing for 1 second. And the reason is I'm just going to add a slide to this, so I don't have any problems here. So new slide. I'll add 2 just in case I mess something up. I messed up today in the morning class. Well, the computer messed up. So it was a pretty big delay trying to get that fixed. Okay, so anyways, this is a very good question for you guys to kind of consolidate or put together all of this information. So, how do we calculate all these types of concentrations? So I'm going to give you an example. Calculate. Now, this is obviously not in your notes, so you can write this down or you can check YouTube later, but calculate the concentration for, let's say, calculate the concentration when 10.25 grams of KCl is dissolved in 300 milliliters of solution. Keyword there, 300 milliliters is our total final solution. Now, the word concentration can be considered ambiguous. Now, if you don't know what that means, it's not clear. Am I asking for concentration in percent? Am I asking for molarity? Well, guys, I'm asking for all 3 of it. So I'm going to say, I'm just going to erase this period here. I meant to say in molarity, percent, and parts per million. Now, I'm going to stop talking in a minute. What I'm going to do is I will give you the formulas. So C is equal to N over V. This one is the mass of solute over mass of solution times 100%. This one is the same thing, mass of solute over mass of solution times 10 to the 6. So I'm going to stop talking. I'll put myself on mute, and I'll be back in 5 minutes at 2:50 to check our answers. If you have no idea what to do, don't worry. Just sit there, try your best, maybe see if you can do 1 of these or 2 of these. If you know what to do, have fun. We'll check your answers in a minute. And for those of you who really are confused right now, in 5 minutes, I'll explain how to do all 3 of these. So I will be back in 5 minutes. All right, have fun. And if you have any questions, let me know. All right, so let's check your answers. I got a couple answers in the chat, which is fantastic. So let's go through this. Let's see what your answers are. Now, one thing, I'm going to have to clear the slide so I have room to write. So let me just write down a couple numbers here. Oops. So I can do this on the next slide. And 300 milliliters. Okay, so I got some answers in the chat. Let's see. So I'm going to go to a new slide here and let's check out our answers. So, excuse me, question number 1, molarity. All right, now I'm starting with the hardest one by far. Molarity is C equals N over V. Now, I obviously do not have N. I don't have moles. So step number 1 is I need to calculate the moles of my solute. So it would be mass over molar mass. So I have 10.25 grams over the molar mass, and I've already calculated the molar mass, which is 74.5513 grams per mole. Remember where this number comes from? The molar mass is the mass of the compound. Basically, I add together potassium and chlorine from the periodic table. And I've done that so many times now, I'm not going to bother doing it again or showing you every step. So let's see what we get here. 10.25 divided by 74.5513. And we get 0.13749. Oops, that's a 9 moles. Now, I can only have 4 significant figures because my question only has 4 significant figures. So we'll round that at the end. We don't need to round it yet. Step 2 is the concentration itself is moles over volume. So I have the moles, 13749. The problem is that my volume is in milliliters. So my question is telling me that I have 300 milliliters. I need to change that to liters. So it would be 0.300 liters. 4 significant figures. All right, and I get my answer. So I divide that by 0.3000, and I get my answer 0.4583 moles per liter. The units for molarity, and honestly, I need to warn you guys, if you do any other chemistry courses, your chemistry professor or instructor will call it concentration. It's just how it is, but technically it's molarity. But if you were in a chemistry course, like a pure university chemistry course, your professor would probably just only call this concentration. So you might hear the word concentration, but this is molarity, and it's about 0.05 or 0.045 moles per liter. Okay, let's look at the next one. So this will be on YouTube, guys. So if I'm going too quick or you need time to write it down, it's obviously going to be put online very shortly. So let's look at number 2, the percent. Oops, I didn't mean to do that. Okay, now guys, the percent is like the percents and parts per million for this question, very straightforward. So let's look at number 2. I'll keep it in purple for now. We're going to look at the percent. Now the percent is the mass of your solute over the mass of your solution times 100%. And actually, we could do even ppm. We could squeeze ppm down here because it's the same thing. Okay, times 10 to the 6. All right, so put in your numbers. Mass of my solute, that was 10.25 grams. Mass of my solution, 300 grams. Remember, if I have 300 milliliters, that's equal to 300 grams. So I take that number, and I'm put it in my calculator, but I'm also going to multiply it by 100 to get my answer. I have a message in the chat. Just let me check that first. Oh, okay. Yeah, I got a good answer in the chat. So let's see. Let's see if you're right. 10.25 divided by 300 times 100. And I get 3.417%. Okay, 4 significant figures. And like, okay, speaking of significant figures, guys, some of you might say, well, hold up, this is only 3 significant figures. But that 100% is like exactly 100. There's no significant figures in 100%, like it's exactly 100. Um, so one thing to keep in mind, like I mentioned in a couple other classes, if you're struggling with sig figs, just pick the smallest amount from the question. And the question gave us 4 significant figures. All right, I got some stuff going on in the chat there. Let me check that again. Okay, more answers. Excellent. All right, so let's see. ppm. Now I'm going to give you a warning. The parts per million is going to be a big number. Parts per million is not designed for numbers this large. I mentioned the other day, parts per million is like when you take a grain of sugar or a grain of salt and you drop it into a bucket of water or a bathtub of water, right? So like I'm just warning you that this number here will be a little larger than normal, but the answer doesn't matter. It's the process. You know, so it's a good example. So I do the exact same thing, 10.25 grams over 300 grams, and I multiply it by 10 to the power of 6 or a million, and I'll get my answer. I should not have cleared my calculator, but anyways, here we go. Okay, so my calculator gives me a gigantic number, but again, that's totally okay. I get 34166 parts per million. And rounding that to 4 significant figures, I would go 34170 parts per million. Now, Naim, or not Naim, I'm thinking of my other class, Abdul Halim, I think. I don't have the chat open anymore. Yeah, Abdul Halim answered the question in scientific notation, which is fine. Whatever you can use like for me, you can use scientific notation, you can use just a normal number, whatever you want. But there you go. There's your answers. Again, that number is a little big for ppm. If you guys are working, in industry, and I'm really speaking to my environmental health and safety students, if I have any, when you test water quality and you're looking for lead or arsenic in water, you're talking like 5, 10, parts per million, sometimes parts per billion, which is even smaller. Okay, guys, so that's it. Well, no, I mean, that's it for chapter 4. It's 3 o'clock. So if you guys will stick around for 10 more minutes, I just want to introduce chapter 5. There's someone in the chat who just said H2S. Why are you saying H2S? H2S, so like hydrogen sulfide?
No, because it's measuring by ppm.
Oh, sorry. Thank you. Yes, Sultan. Sorry about that. You are correct. Yeah, you could measure H2S, which is a very toxic gas. This is something that when you work in the oil and gas industry, you would really take measurement of H2S because it can be a health hazard, hydrogen sulfide. And yeah, Sultan, that's a perfect example. The amount of gas that you might find in the air around a refinery would be probably parts per million. And I don't actually know the toxic level, but once the H2S gets to a certain parts per million, or parts per thousand maybe, it can become very dangerous to humans. Yeah, so that's a perfect example, especially for my engineers in here. All right, cool. So give me 10 minutes maximum, and you guys will be out of here today. I just really want to introduce for you chapter 5. Okay, I'm excited to start chapter 5. For realistically, chapter 5 is our last basic chapter. There is a chapter 6, but chapter 6 is something we could do in maybe 2 classes. Chapter 6 is very, very small. Chapter 5 is going to take us maybe a week or two. Well, okay, not a week. Who am I kidding? Chapter 5 will take me maybe 2 weeks or more to do, but it's really one of the most important units in this course. Why is it important? Well, there's a lot of reasons why. I mean, it's about chemical reactions. I mean, what is chemistry if you don't study chemical reactions? So think of this course. Think of like what we've done in this course so far. Chapter 1, we did kind of like an introduction to chemistry. Chapter 2, we did a little introduction to the periodic table. Chapter 3, we started learning about naming and bonding. Chapter 4, we used some calculations. And all of this is building up to really what's one of the most important parts of chemistry is the chemical reactions. Chemistry is the study of matter. And unlike physics, so physics kind of talks about the universe's interaction with matter, how fast something is going, gravity, acceleration. Physics is a lot more than that, but at a, college level, you're kind of talking about interactions, momentum, velocity of matter. Chemistry at the introductory level is about the conversion of matter to something new, a chemical reaction. Okay, so now that we know how to name chemicals, we know how they're bonded, we know how to do some calculations, we're going to look into this concept of a chemical reaction. So all I really want to do today is, now this seems like a lot, but it's really not. I want to define what a chemical reaction is. I want to list or I want to give you a list of changes that show a chemical reaction has happened. And then I want to explain to you just a little bit about what a reaction would look like on paper. And honestly, I did this with the group this morning. This does not take long. Okay, so a chemical reaction, what is it? Complicated, this isn't a complicated definition. This is like the medium definition. Chemical reactions are when elements or compounds react to form new chemicals. Okay, so really what's happening is old bonds are breaking, new bonds are forming. The key thing to remember for a chemical reaction is that something new has to be made. So just imagine now you rip a piece of paper in half. It's still paper. Okay, paper is made of different things. I don't know exactly what besides cellulose from like plants. But if you rip that in half, you're not changing any molecules. You're not going to rip a molecule in half. Splitting molecules apart is something well beyond the average person's ability. So when you rip a piece of paper, when you cut something, when you break glass, you're not creating a new chemical. However, when you do something like fry an egg, toast a piece of toast, burn a candle, you are making something new. You're completely changing that chemical. Like, think about when you cook an egg, you cannot go back to the original egg. It is cooked, it's done, like it's finished. You toast a piece of bread, it's cooked, right? You've browned it. A chemical reaction has taken place. Think of even like, I know this is a bit kind of gross, but like, think about fruit or vegetables like going bad in your house, in your kitchen. Once a fruit or vegetable has spoiled, I mean, that's it. It's done. You can't fix a apple that's gone rotten. You just have to throw it away or compost it. So these are all chemical reactions. We're making something new. Rust is a good example of a chemical reaction. Now, you can clean rust, but in terms of like turning the rust, like say you had a piece of iron and the iron rusted, you can definitely clean the rust and remove it, but you can't not easily turn the rust back into the iron. What rust is, and so I'm answering your question here. The question is, if people can't see it, is rust formation a chemical reaction? And if so, what is the product? It is a chemical reaction, and the product is iron oxides. I think it's iron 2 or iron 3 oxides. Let's see. My brain. Well, so like rust, it just says it's iron oxide. I don't know if it's predominantly iron 2 oxide or iron 3 oxide. But the way rust works, or the way it happens, is it's a chemical reaction between the iron and oxygen, and you typically in the presence of water or moisture. It's an electrochemical type of reaction or redox reaction, which we'll talk about later actually. And I just looked it up. It's iron 3 oxides are typically your product of rust. So iron gets together with oxygen, and a little bit of moisture helps the reaction happen. And basically, it's a form of corrosion. So that's a really good question. Any of my chemical engineering students in here, you're going to do courses and units in some of your future classes about rust, or more specifically about corrosion. So yeah, that's a really good question. So yeah, it is chemical. It's a reaction between iron and oxygen, and it makes iron 3 oxide. Okay, so very quickly now, this is easy. Oh, and well, I should say this is easy, but guys, wink, wink, all right? Big winky face here. Know the signs of a chemical reaction. On a test on the final exam, we might ask you to list some signs that a chemical reaction happened. So you're in the lab, you're in the kitchen, or you're watching something happen on television. How do you know it was a chemical reaction? How do you know something new chemically has been formed? Well, I think there's 5 or 6 ways. The first way is a change in temperature. So burning a candle, burning a log. Sometimes when you mix two chemicals together, they can feel very hot or very cold. A change in temperature typically means that a chemical reaction happened. You will look at these two terms in chemistry 1121. You don't need to know them. And if you're not doing any more chemistries, don't worry about it. But if you get to chemistry 1121, we do a whole chapter on this. It's called thermochemistry. And we look at different types of reactions. Some reactions release heat, like burning a candle. Some reactions absorb heat, which is a little bit more hard to kind of give you an example of. But sometimes in like hospitals, they have cold packs. They break these cold packs and a chemical reaction happens and they turn very cold. That's another sign of a chemical reaction. So, sign of a chemical reaction number 1. Sorry, my phone was ringing. Sign of a chemical reaction number 1, change in temperature. Signs of a chemical reaction number 2, you see light or sparks. Now, an example of this, you guys saw me do this for you in lab number 2. Remember when I mixed the sodium? Oh, my pen is hating me today. Remember when I mixed the sodium and water and we saw it go crazy in that beaker? And I say me, you would have done it with me or Michelle or Mohammed or whoever your instructor is in the lab. In lab number 2, we mixed sodium metal with water, and if the room was dark enough, you would have seen light. Okay, so signs of a chemical reaction. Temperature change, there's light, there's a color change. So a color change you guys have seen in labs before. You mix two chemicals, it turns white, it turns purple, it turns blue. That's a chemical reaction. Think about when you bake bread or cook toast, or you cook an egg, cook a chicken breast. They change color, and that means a chemical reaction has happened. Sometimes when you mix two chemicals together, you'll get a solid being formed. You did this in lab 8 this week in part D. So if any of you have done your lab this week, I would assume most of you have. In part D, you made a new solid called a precipitate. And then the final one is sometimes it just makes a gas. And that is also the sign of a chemical reaction. Now, I wouldn't recommend this in the chemistry lab, but in real life, you can often tell if a chemical reaction is happening because you smell something. When you smell something, the odors, the gas vapors are coming to your nose. So if you're doing something, and again, and cooking is a prime example of this. If you're frying garlic or cooking, chicken or potatoes or something, and you smell it, it's likely due to a chemical reaction because the gas coming off of the process carries odor with it. All right. I'm pretty much done for today. I'm really sad because I didn't get as far as I wanted to. Oh, you have a good, there's two things I'll mention because there's two good questions in there. I might just give you, no, I think I probably will stop here. Yeah, I probably will stop here. I was, in the other class, I talked about this, but it's only 5 minutes work, which I can do tomorrow. So we'll kind of hold off on this part. But I will get to the questions and then we're done. So where's my chat? Question number 1 is from Abdul Halim. And this is a good question. If you only see one of those signs, is it a chemical reaction? The answer is basically yes. And like, here's the thing. There's so many exceptions in the world. Just because something feels warm doesn't mean there's a chemical reaction. It could be warm because it's in the sun. It could be warm because, like there's so many factors. Like I had students this morning talking about like, well, when you boil water, it's hot. Is that a chemical reaction? It's not a chemical reaction. Boiling water is not changing chemicals. You're just making the water hot. You're making it go faster. So to really kind of answer your question, Abdul Halim, if you mix two chemicals together and nothing happens, no temperature change, no light, no color, no solid, nothing, probably not a chemical reaction. If you mix two chemicals together, so again, I'm not talking about like putting water in the kettle on the stove. I mean, I'm mixing two chemicals together. If you see one thing happen, temperature change, gas, a solid being formed, any one thing, it is sign of a chemical reaction. So long story short, yes, if you see one thing, it's a chemical reaction. For the other student there, Mohammed, if you missed the lab and you have an excuse, send that to your lab instructor. It might be me, it could be Michelle, but if you have sick leave, you should send it in to your instructor. Okay, guys, sorry, I'm just sipping on coffee here, trying to stay awake. That's it for me today. If you have any questions, let me know. I'm going to stop the recording now and we'll move a little deeper into chapter 5 tomorrow. So have a great day and I'll stick around if you have any questions. All right, goodbye.